Okay, we are in section 2.2, instantaneous velocity and speed. And let's go to the next slide. Oops, I'm not quite ready. All right. Often we need to know the velocity of a particle at a particular instant in time. What does it mean to talk about how quickly something is moving if we freeze time and talk only about an individual instant? If time interval has value of 0, then the displacement of the object is also 0. Average velocity would seem to be 0 divided by 0. How do we evaluate that ratio? In the late 1600s, the invention of calculus gave us the tool to answer this question. Consider figure A. What is the particle's velocity at t equals 0? The average velocity from A to B is the slope of the blue line. The average velocity from A to F is the slope of the longer blue line. Focus on the short blue line. Imagine the sliding point B to the left along the curve toward point A. Figure B, that's a blow up of that small section. The line between the points becomes steeper and steeper. As the 2 points become extremely close together, the line becomes the tangent line to the curve, the green line. The slope of the tangent line represents the velocity of the car at point A. So the instantaneous velocity is the v sub x is the limiting value of the ratio of delta x divided by delta t as delta t approaches 0. The v sub x is defined as the limit as delta t approaches 0 of delta x over delta t. Of course, delta t can never be 0 because then it would become undefined. In calculus notation, this limit is called the derivative of x with respect to t, written dx dt. Okay, the instantaneous velocity can be positive, negative, or 0. When the slope of position versus time graph is positive, as in the first 10 seconds, Vx is positive and the car is moving toward larger values of x. After point B, V sub x is negative because the slope is negative and the car is moving toward smaller values of x. At point B, the slope and instantaneous velocity of the car, the instantaneous velocity is 0, meaning that the car is momentarily at rest. This was where the car went forward and then started to back up. At some point, it has to be 0. Velocity designates instantaneous velocity. For average velocity, use the word average. The instantaneous speed of a particle is the magnitude of its instantaneous velocity, no direction. As an example, one particle has an instantaneous velocity of 25 meters per second. Another particle has instantaneous velocity of minus 25 meters per second along the same line. Both have speeds of 25 meters per second. So there's a difference between speed and velocity. Speed is always a positive magnitude. Okay. So here is a, let me make sure I was, yes. Here's a quick quiz. Members of the Highway Patrol are more interested in your average speed or your instantaneous speed as you drive. What do you think? It's your instantaneous speed. All right. Regardless of your speeds at all other times, if your instantaneous speed at the instant is measured is higher than the speed limit, you may receive a speeding ticket. So it's your instantaneous speed that they're interested in. Okay. Consider the one-dimensional motion of a ball thrown directly upward, which rises to a highest point and falls back into the thrower's hand. Are there any points in the motion of this object at which the instantaneous velocity has the same value as the average velocity over the entire motion? If so, identify the point. Can you think of any points in the motion of this object at which the instantaneous velocity has the same value as the average velocity over the entire motion? It's at one point at the top of the motion when it actually becomes zero. The average velocity for the thrown ball is zero because the ball returns to the starting point. Therefore, its displacement is zero. There is one point at which the instantaneous velocity is zero, at the top of the motion. At the top of the motion, yes. Okay, consider the one-dimensional motion of a race car which starts from rest and speeds up to 100 meters per second. Are there any points in the motion of this object at which the instantaneous velocity has the same value as the average velocity over the motion? Oh, I'm sorry. Yeah. I was reading that it hadn't advanced yet. Consider the one-dimensional motion of a race car which starts from rest and speeds up to 100 meters per second. Are there any points in the motion of this object at which the instantaneous velocity has the same value as the average velocity over the entire motion? At some instant, somewhere between 0 and 100 meters per second. The car's average velocity cannot be evaluated unambiguously with the information given, but it must have some value between 0 and 100 meters per second, because the car will have every instantaneous velocity between 0 and 100 meters per second, and sometime during the interval, there must be some instant at which the instantaneous velocity is equal to the average velocity over the entire motion. Okay. Consider the one-dimensional motion of a spacecraft that drifts through space at constant velocity. Are there any points in the motion of this object at which the instantaneous velocity has the same value as the average velocity over the entire motion? If so, identify the points. Because the spacecraft's instantaneous velocity is constant, its instantaneous velocity at any time and its average velocity over any time interval are the same. For all positions of the spacecraft, this is true. Okay. Oh, I messed up. All right. A particle moves along the x-axis. Its position varies with time according to the expression x equals minus 4t plus 2t squared, where x is in meters and t is in seconds. The position time graph for this motion is shown in the figure. Because the position of the particle is given by a mathematical function, the motion of the particle is known at all times. Notice that the particle moves in the negative x direction for the first second of motion, is momentarily at rest at the moment t equals 1 second, and moves in the positive direction at time t greater than 1 second. Determine the displacement of the particle in the time interval t equals 0 to t equals 1 second, and t equals 1 second to t equals 3 seconds. Now, from the graph, let's form a mental representation of the particle's motion. Keep in mind that the particle does not move in a curved path in space, such as that shown by the red-brown curve in the graphical representation. The particle moves along the x-axis in the dimension as shown in the lower figure. Below that graph, you see the BACD, that's in part B of the graph. At t equals 0, is it moving to the right or to the left? It looks like it's moving negatively. During the first time interval, the slope is negative, and hence the average velocity is negative. Therefore, we know that the displacement between A and B must be a negative number having units of meters. Similarly, we expect the displacement between B and D to be positive. In the first time interval, set T initial equal to TA, which equals 0, and T final equals TB equals 1 second, and use the equation x equals minus 4t plus 2t squared to find the displacement. And if we substitute the 1 into each of these, we get that it's minus 2 meters. For the second time interval, t equals 1 second to t equals 3 seconds, set t initial equals tb, which is 1 second, and t final equals td, which is 3 seconds. And so you get, if you do the substitution, you get 8 meters. And notice how they're substituting for x final and x initial. Okay, these displacements can also be read directly from the position time graph. If you look at B and D, you'll see from -2 to 6, you get 8. Okay. Now, calculate the average velocity during these two intervals. In the first time interval, use this equation with delta t equals t final minus t initial equals tb minus ta equals 1 second. The average is the 2 meters divided by 1 second. That's -2 meters per second. In the second time interval, delta t equals 2 seconds. And you'll see that it's +4 meters per second. These values are the same as the slopes of the blue lines joining these points in the graph. The slope equals -2 meters per second from A to B, and +4 meters per second from B to D. Okay. Now find the instantaneous velocity of the particle at t equals 2.5 seconds. Calculate the slope of the green line at t equals 2.5 seconds, point C, by reading position and time values for the ends of the green line from the graph. So he's got the 10. The green line goes all the way to 10 and down to -4, and he's estimating the values is 3.8 seconds minus 1.5 seconds. And so your instantaneous velocity at that point is 6 meters per second. Notice that this instantaneous velocity is on the same order of magnitude as our previous result. That is a few meters per second. Is that what you would have expected? Okay, this ends our discussion of section 2.2. The next sections where we will discuss are sections 2.3 and 2.4 together in one video, analysis model. Okay.